My name is Emma Doring, and this is my Physics 2 Lab 2 on the magnetic field of a bar magnet. The purpose of this lab was to figure out how distance affects the magnetic field due to a bar magnet at an observation location. The assumptions I made were that the bar magnet is a magnetic dipole, my phone was not rotated, bumped, or tilted during the experiment, and there were no outside magnetic fields present during the experiment. The formulas I used were the Biot-Savart law, both off-axis and on-axis, as well as the formulas given for distance dependence. I used the off-axis magnetic field formula to calculate the off-axis magnetic field of the bar magnet, and then used the on-axis formula to calculate the magnetic field on-axis of the bar magnet. And then for the distance dependence formulas, I took the natural log of the first equation in order to graph my data as a line that had a slope of n, so a slope of the distance dependence, and an intercept of ln k, and this allowed me to obviously calculate n and then calculate the magnetic dipole moment. The general results of the experiment were that the distance dependence was -2.5661, the magnetic dipole moment was 6.92 amperes times meters squared, the computational off-axis magnetic field was 5.64 e -5 Tesla, and the experimental off-axis magnetic field was 2.26 e -5 Tesla. In my experiment, the system was the bar magnet and the surroundings were Earth and the magnetometer sensor. The steps that I followed were I used the magnetometer app to align my phone with Earth's magnetic field. Then I found the magnetometer sensor. Then I found distances from the bar magnet at which the magnetic field on axis was 20, 70, 120, 170, and 220 microtesla. I used the given Excel template to make a log graph of my data and find the distance dependence and the magnitude of the magnetic dipole moment. Then I found the off-axis magnetic field and used GlowScript to write a code that modeled both the on-axis and off-axis magnetic fields. The results of the experiment are shown here. On the left is my Excel sheet. You can see the results of the distances for each of the on-axis magnetic fields as well as the off-axis magnetic fields, and then my graph that shows the data as a line and the formula that has n as the slope and k as the intercept, or ln k as the intercept. And then on the right you can see how I use this to calculate the magnetic dipole moment. For the computational model, the initial conditions were the magnetic dipole moment and the d-perp distance from the experiment. So in order to generate the on-axis and off-axis magnetic fields and the distance d, I entered my magnetic dipole moment from the experiment first, and then created a function dipole b for the magnetic field of the magnet. Then I set observation locations both on-axis and off-axis and created arrows to represent the magnetic fields at each of these. Lastly, I entered the average d-perp to calculate the distance d and created an arrow to represent the magnetic field at 45 degrees from the magnet. So here are my coding results. You can see the magnetic fields on-axis and off-axis at the bottom, and the d distance and magnetic field off-axis on the right, and then the arrows show or represent the magnetic fields. The conclusions I made were that when the magnetometer sensor is far from the bar magnet, the x direction of the magnetic field is near 0, and then as the sensor moves closer, the x direction of the magnetic field increases. The experimental and computational 45-degree magnetic fields didn't agree very well. The difference was about 3.4 e to the -6 Tesla. Possible sources of error: I could have misread the distances during the experiment, I could have accidentally moved my phone, or I could have had outside magnetic fields near my phone. If I didn't orient my setup to compensate for magnetic north, the magnetic field of the magnet would not be perpendicular to that of the Earth, and then the resulting net magnetic field would include both the Earth's and the magnet's magnetic field, and I would have to subtract the Earth's magnetic field. And then if I used two identical bar magnets stuck together end to end and redid this, the magnetic field would be greater, so the distances between the magnetometer sensor and the magnets would be less for each magnetic field. That's all. Thank you.